Hello and welcome to another episode with the Women of BSV. Today we are speaking with the Chief Technology Officer of a clean energy company that is pioneering a unique technology that is poised to transform the global power industry. At SRI International in Berkerly, California, Robert Goddess and his team have tapped the power of a nuclear reaction with absolutely zero radioactive waste or harmful emissions. In the lab, their hot hydrogen tube reactor has all the data and evidence to prove replicatable results over and over, where you can turn this thing on and off, up and down, and even set it like a thermostat. The final funding and the Wright partnerships are the only things that are standing in the way of this commercial-ready technology that produces truly clean energy at an extremely low cost that's been designed to go right into mass production. Since the mining of BTC uses more electricity than many countries, we feel an obligation to look into how we could harness this excess heat for the practical application towards mining operations in BSV. So thank you so much for enlightening us all about this today, Robert. Welcome to the show.
Thank you. Great to be here.
We're very excited. So where would you like to begin?
Well, it's kind of up to you guys where you'd like to begin. I mean, I can give a quick overview of how I view the technology and where it can go, what it can do for the world.
Absolutely. I'd love to start that. And just as you explain, really focus on how it can be applied towards mining operations, and we'll get it to the right people that can maybe, explore that option.
Excellent. So even this morning I was reading a Deal Book is a sub-publication put out by the New York Times, and it was a big piece on the energy usage of cryptocurrency in general. And I tweeted I tweeted the article, said, you guys really need to talk to Brillouin Energy, because what we're developing is nuclear energy, as Casey mentioned earlier, is nuclear energy kind of minus the nuke. In other words, we use most nuclear energy right now, and in fact, all nuclear energy right now uses very heavy atoms beyond the sort of the peak of the binding energy. If you look at a chart of the nucleotides binding energy, nickel and iron are at the top. And as you go beyond nickel and iron, the binding energy gets smaller. So when you split them, the binding energy goes up, and that difference in binding energy comes out as heat. That's how nuclear energy works. Brillouin Energy is using hydrogen, which is the smallest atom. Nuclear from the nucleus is the smallest in the periodic table. Atomically, it's actually about twice the size of helium. But we build that up to helium, one neutron at a time, using this technology. And that releases nuclear energy, but without the radiation. So when you split a uranium atom, it's enough energy to loft a single grain of sand several inches into the air, numerous centimeters into the air. This technology won't loft that grain of sand quite as high, forming one helium atom, but it's way, way, way less mass. So the exhaust product from this technology is helium, which is a mass of 4, versus uranium, which starts with a mass of 235, is the fissionable version of uranium. And the end result of all the very, very dangerous pieces left over after it splits is less, quite a bit less than the mass of a single helium atom. But then you have all that really dangerous stuff that's left over. So, and even before you split it, some of it splits on its own just naturally. So you always, just U-235 is uranium in period, is rather dangerous. You won't want to carry it around in your back pocket, as opposed to hydrogen, which is ubiquitous. If you were to fill this coffee mug with water, the hydrogen contained in that would be enough to power all 5 boroughs of New York City for probably more than a week. And that's including the subways, transportation, all the pumps to, pump the water out of the subways and subterranean locations within the city, everything, heating, lighting, ventilation, air conditioning, everything. So, and it's also extraordinarily scalable. It's been designed from the get-go to go into mass production. What we're working on right now, much more slowly than it really should go, just from a lack of space and access to equipment, is the material science that will allow us to go into mass production. So that's Brillouin Energy, and it's extremely scalable also. So right now we're working with catalyst rods that are 18, 19 inches long. Sorry, there's probably a lot of people that would prefer it in centimeters, 2.54, just multiply it.
That's right, we still do inches over in Europe, don't worry.
Don't worry. I've got double tape.
So anyhow,
can I ask a question, Robert? Can I?
Absolutely, please do.
So the probe or whatever it is you're using, what is that made of? What is the element that you're heating? Is that like a zinc or something?
Oh, the catalyst?
The catalyst, yeah.
The catalyst is nickel.
Nickel.
Yeah, which is $8 a pound, $8 for a couple of kilograms.
And does that get deteriorated in the reaction?
No.
Or?
It is used as a catalyst. So a catalyst is something that lowers the energy barrier for a reaction, used extensively in chemistry. But in this case, we're using it as a nuclear catalyst.
And so are you pulling protons out of the hydrogen and making neutrons? How is this going?
So hydrogen, water is H2O. So there's two hydrogen nuclei, 2 hydrogen atoms and 1 oxygen atom. And just simple electrolysis will split those 2 hydrogen atoms off of the oxygen atom. And that is really your cleanest source of hydrogen for use in this reaction. Once it's in the nickel lattice, I can go really deep into, but I won't for this audience. We use a shock, sort of like a hammer, to convert the proton. It takes energy to turn a proton into a neutron. It's very endothermic. It absorbs energy to make that transition. Because it's endothermic, it's converting that energy into mass. The neutron that forms is really, really cold. I mean, like even colder than the Bose-Einstein condensate, if anybody has heard of that. But those are really cold. And so when you have a really cold neutron, it has a really high cross section, which means it's more than happy to bind with anything that comes within the nuclear binding distance. And it's that binding energy that gets released as heat. Heat is phonons is the technical term of how the energy comes out. So we've had catalyst rods run for nearly 2 years. That the one that we had running for 18 months, more or less continuously, got broken and broke the end off of it. When we pulled it out, it was pristine. It looked way better than when we put it in because it's operating in a pure hydrogen environment. So it strips all the oxides that gives nickel kind of a dullish color, and it was bright, very, very, very clean.
Cool.
And what is the name of your company?
Brillouin, Brillouin Energy. And
where does the name come from?
Yeah, so there was a very famous conference back in the 20s, the Solvay conference, where they decided on the standard model physics, quantum mechanics. And Leon Brillouin was the third in a line of very, very famous French physicists. And he came up with a mathematical description of metals called the Brillouin zone. And it's used extensively in study of thermodynamics and quantum mechanics. Really, thermodynamics is probably the most common area of use for that.
How many years of your life has it taken to get to this particular point of the project?
So,
I mean, this sounds to me as though it's a lifelong project.
It's taken longer. I didn't realize how difficult it was going to be to raise money for this project. So I actually figured the physics out in 1992. It's probably before many people who will watch this were born.
That was when you were with Xerox, right?
Yes, that's right. That's right. I was working at Xerox Engineering Systems. It was 92. Yeah, it was just the name of the company was actually Versatech, but it was a wholly owned subsidiary of Xerox Engineering Systems. And yeah, the engineer that there were a group of us, a group of engineers talking, and I said, I don't understand, why don't we have flying cars yet? And one of the engineers said, oh, what are you going to power that with? Cold fusion? Ha ha ha. I basically lost faith in the people on the television in the 70s. And so I'd completely missed that whole fiasco with Pons and Fleshman in 1989, which was like 2 weeks before the Exxon Valdez ran aground in one of the largest oil spills on record. And I said, I don't know what you're talking about. He said, oh, Pons and Fleshman, the University of Utah. I'm like, he said, well, they were doing electrolysis with a palladium cathode and a platinum anode. Mm-hmm. And they said they were getting nuclear energy out of it. They said they were producing fusion. They said, palladium cathode. He said, yeah. I said, that's a really, very well-known hydrogen catalyst. He said, well, they use it to filter hydrogen. I said, filter hydrogen? He said, yeah. I said, so if you put a mixture of hydrogen and helium on one side of a palladium filter, only the hydrogen will go through. He said, yeah. So remember earlier I said hydrogen is actually about twice the size at the atomic scale, not the nuclear scale, but at the atomic scale. Hydrogen is about twice the size of helium because the one proton, you can only have 2 electrons in any orbital. So in the 1s orbital, you have a spin up and a spin down electron. So a single proton in hydrogen can only hold that electron about half as tightly as the 2 protons can hold the 2 electrons, because there's essentially no screening between the 2 electrons. So both electrons see more or less a charge of 2. And so it's about almost half the size. It's a little more than half the size of hydrogen. The helium won't go through, but the hydrogen does. And I was, had known this for many years. And I said, oh. And I said, oh yeah, they used palladium was the first proton exchange membrane in the Apollo fuel cells. He said, yeah. I said, oh, I know what's going on. My brain has all these random things bouncing around in it all the time, and I realized what had to be going on. So that was 1992. And I said, oh, I know what was going on. I said, no, it was completely debunked by Caltech and MIT. I said, no, I'm pretty sure they were onto something. He said, well, it's so obvious to me. Surely somebody working in the field has already, recognized what's happening. And, if nobody's got a product on the market in 10 years, I'll build it myself. He said, yeah, right. Fast forward to so that was 92. So fast forward to 2002, and the internet came online in 93, or the web came online in 93, and I started looking for information. I'm like, man, nobody is going down the right path here. So finally, in 2002, 10 years later, I'm like, okay, I'm going to have to do this myself because this has to happen. And so I went into the lab. I'd gotten I took a job with a company called Energy Line that got bought out by a Chicago-based company and became very dodgy. Stodgy, not dodgy. They're actually a very solid company. But stodgy energy energy control
Right.
systems company. And but meanwhile, when Energy Line hired me, they allowed me to modify the NDA and develop my own technology in their lab. They had a great lab. They weren't willing to pay me that much, but they had a really great electronics lab. So I worked developing all the technology that was going to be needed to drive the reaction, the underlying physics of the reaction. And then in 2002, almost exactly 10 years after I figured out the underlying physics, I over the course of like 6 weekends going into the lab, and every time they had a problem they needed solved, there's always more than one way to solve a problem. I would solve the problem in a way that actually helped me further my technology as well. And so I cobbled all these various things that I had designed for them together. And after it took 6 iterations, and I was actually able to show that I could reliably and repeatably get as much thermal energy into this, more thermal energy into the system than I was pulling electricity out of the wall. And so I'm like, okay, this really works. And so that was when I actually started working on trying to build a company. That was in 2002. I didn't quit my day job until 2005. So from 2005 until 2009, I spent about half my time trading stocks to keep myself afloat, and spent the other half of my time working on developing the IP and working on building a new team. Took me 3 times to put together a team that formed Brillouin Energy. And so yeah, it's been really
long
time.
journey. Yeah, I was going to say, it sounds, you're talking about Fleischmann in the 80s, and they so comprehensively discredited cold fusion, the whole concept, didn't they? Nobody wanted to touch it with a barge pole. So it's no wonder that it's been difficult to, convince people to invest in it since. But it does seem to be coming of age now, though, don't you think? There's a lot of hydrogen technology maturing at the moment. I mean, I myself have a hydrogen producing water bottle. I normally have it on my desk, but I don't right now. That's got a PEM membrane in it, like you're talking about.
Mm-hmm.
And the thing about hydrogen is, even in really tiny quantities, it has the same sort of energy giving effect inside the body. So I've been using hydrogen medicine myself now for about 3 or 4 years, and I've got my health really back on track because of it.
Excellent.
So it has all sorts of applications. I mean, the thing about hydrogen is sort of pure energy, isn't it? And it makes up the majority of the universe, right?
You guys are giving me chills. I got chicken skin on that one.
Hydrogen's very special substance.
Well,
for sure.
It is. It is the most common element in the universe. Einstein actually said the only thing more common than hydrogen is human stupidity.
Yeah.
But one of the great things, I walked to and from my lab in Berkeley, and do not walk, and I'm looking down. There's no cars for blocks and blocks, and it's like approach the light and it's red, and it's got the red hand, and there's all these Berkeley students that are like standing the light. I'm like, I walk across, and there's this like bum. He's like sprawled out on the sidewalk, kind of looked like Bill the cat. And I said, only thing more common than hydrogen is stupidity. He goes, no, hydrogen. Ainstein actually said, he like knew the exact quote.
So even the bums
Berkeley.
are super intelligent now.
Exactly. Well, did you ever see Real Genius?
That name sounds really familiar. I may have.
With Val Kilmer? Yeah, that makes me think of that Caltech and all.
Yeah.
But it sounds like you are harnessing the magnetism of the bond in the atom.
Yes. Yes. It's and hydrogen. You know, you see a lot of things about hydrogen and fuel cells and things like that. Those things use hydrogen as chemical energy. So if you take a pair of hydrogen molecules, H2, and you run them through a fuel cell, the total energy released, some of it comes through as electricity, some of it comes out as heat. But the total energy of using those 4 hydrogen nuclei as a chemical fuel is about 5 electron volts, about 5 eV or 5 units of energy. When you run those same 4 hydrogen atoms through this process, it releases 27 million units of energy. So you've got 5 versus 27 million units of energy. Big difference between using hydrogen as a nuclear fuel versus using it as a chemical fuel. So that's why this much hydrogen would be enough to power the hydrogen in this much water. You were to electrolyze all the water, fill this up. It would be enough to power your, the dryer in your house for a couple of hours versus the entirety of New York City for more than a day.
That's incredible.
What's the biggest resistance and who's that come from?
So,
I mean,
the biggest resistance typically comes from academics, especially in the nuclear field. And there's something called with the U.S. National Labs. There's something called a TAP, or Technology Assistance Package, where you get 8 hours of a researcher's time. And so one of my technical advisory board members was doing a lot of work with Pacific Northwest National Labs. And the researcher that he was paying on a regular basis to do research for him, he got me a TAP with them, and he said, well, what would you like to simulate? I said, well, I'd like to simulate the first Brillouin. He said, no. We can barely do a full simulation of H2. What's the simplest thing that people, that you would like us to prove? I said, prove that if you put a proton and some electrons in a box, when you make L, or the length of an edge of that box, small enough, just confining those pieces into a small enough area will make the energy level high enough that it will form a neutron, and that neutron will form at a very low energy level. He said, that'll never work. I said, great, prove it. He said, that's what you want to use that's what you want your TAP to be. I said, yeah. He said, okay, fine. And he comes back 3 weeks later, he says, yeah, actually that works. I said, I know it works. And that's your reaction is exactly why I have so much trouble when I'm talking with PhDs about this, is nobody thinks it'll work. But I know that it does, because if it didn't, my reactors wouldn't work, but they do. I said, I'd like to do a more extensive work with Pacific Northwest Labs. And he said, well, it's really expensive. At the time, I actually had, a fair amount of money in the bank. I said, well, how much work could I get done for $100,000? He said, oh, you can get a lot of work done for $100,000. I said, great, let's put together a package and I'll fund it. He was all excited. And I called him back, 3 weeks later. I said, what's happening? He said, I'm working on it. I said, okay. I said, you might be running into some resistance on this. He said, well, I'm working on it. I said, okay. I called him back the next week. He said, yeah, I seem to be getting some serious headwinds on this project. I said, well, let's keep going, because I'd really love to fund, more work on this. Call him back the next week. They're not going to take your money. They don't want anything to do with you. Go away.
As you can imagine, this challenges the current energy sector quite a bit. So
Yes.
I remember you saying in one of our previous conversations how this can take like existing nuclear facilities and completely, run them with your technology. Can you explain that a little bit?
Sure. So I'm not sure it would be economically worthwhile to convert an existing nuclear facility because you've got to deal with all that radioactive waste that they've all got lying around. But you could certainly go in and repower an existing power plant with this technology. Anything that's currently using steam or even supercritical CO2, you could take this technology and repower that power plant. This technology will be extraordinarily disruptive to the energy ecosystem of the planet in general. But I'm not getting pushback from oil, but the biggest pushback is coming from the people working on hot fusion. People, Livermore actually had a researcher at Los Alamos National Labs do a first principle test of my hypothesis and was successful. And I said, well, can you publish it? He's like, well, the lab really doesn't like me working on this. I said, well, any way I can help. He said, well, I'm going to be retiring and I'll do more tests at my house. I said, great. And he said, yeah, so I can do this, but I can't publish because they're going to cancel my emeritus status at the lab, which, all his friends, he's been working there pretty much his entire life. They're not going to allow me, they're going to cut off my access to the lab completely if I publish this. Because our government here in the United States is spending plus or minus, a few $1 million, $500 million a year on hot fusion research. And this will essentially cancel that. It won't cancel it, but it will blow the cover of using that research for civilian energy purposes. You talk to anybody working in any of these hot fusion programs, if they know what's going on, the root of what that research is about is stockpile stewardship, nuclear weapons. It's about nuclear weapons research. It's
right.
not about.
They're trying to make, things that go bang.
Yeah.
And is that the difference between what you're doing and CERN? Because I recall CERN is the hydrogen reactor, right? In Switzerland?
So CERN is a large nuclear research facility. It's the largest nuclear research facility, atom smashing machine in the world right now. And a tiny percentage of what CERN is doing. So they've got, I don't remember how many miles around it is, but I mean, it spans, I think, Switzerland, France, and maybe some other country.
It's crazy big, yeah.
Yeah, it's crazy big, and so they use magnets because you pass a charged particle through a magnetic field and it bends, and so they've got this massive ring, and they accelerate those particles to near light speed in opposite directions. So they're going like this, and then they smash them, bang! They smash them into each other, and they have detectors, 3 Atlas, CMS, and I think 1 or 2 other massive detection facilities where they can cause these collisions. And they look. It's like you take a pocket wash and you put it on the tail, and you bam, and they look at where all the pieces fly off, and how fast they're moving and the directions that they're traveling and the curves from the magnetic field that they're going through and everything. And so it's
different from where you are pulling the
so that's the underlying
force that is connecting the atom together.
Right. Yeah. So they're breaking things apart, and it's fundamental research about the nature. So the Higgs boson, probably everybody's heard of the Higgs, the God particle that gives everything mass. So that was validated. They found that and were able to validate that they found that at CERN, at the super collider there. So that's what that is. What we're doing is we're taking protons, we're turning them into neutrons. So if you have two charged particles, they don't want to get together. So there's a big energy. There's a wall. There's a wall between them that is the Coulomb barrier, because they're both positively charged. This one turns into a neutron. That wall is like, it's like dropping your shields. It's like that wall has gone away. Now another proton, deuteron, or triton can tunnel into where that neutron just formed, and they bind. And that binding energy is what we're tapping into.
Wow. So how do you harness that binding energy? How do you take that out? And also, what goes into your machine? Do you put water in there, or what is going into your invention?
Right. So what goes in is hydrogen gas.
Okay. And, just like balloons.
Is it plasma or is it gas?
No, it's gas. So in a fuel cell, a proton exchange membrane, what happens is the proton goes through the material. The electron takes a different path and goes through your load. That's how a fuel cell works. So, but the electron, for every 5, 6 protons that enter into the metallic lattice, only one electron goes in. So inside the lattice, it kind of distorts the shape of the way the electrons are orbiting. Most everything is empty space, whether you know it or not. Seems solid, but it's mostly empty space.
So is it that you're just condensing the hydrogen? Are you forcing it into a small space? What's the kind of the thing that breaks down the bonds?
Right. Well, so that, like my tap with Pacific Northwest National Lab showed that most people have played with a ping pong ball on a table, and as you move the paddle closer and closer, the speed of the ping pong ball speeds up. It's like using water in pipes as an analogy for electricity that breaks down, fairly quickly. But as you confine things into a smaller and smaller space, the energy level goes up. And so hydrogen is already confined into a pretty small space within the lattice. And remember I said we use a shock, like a hammer hitting it. So we use an impulse function or a rogue wave of electricity.
Oh, I see.
And so the hydrogen is kind of trapped in this location in the lattice, and we have this tidal wave of electricity that goes through and further confines it. Further confines the hydrogen in there, but it's also trying to push the protons or the nuclei of the lattice closer together. And the energy level, if you look at an energy diagram where this is energy and this is the location of the atoms relative to each other in there. So this is 0. And there's a point down here where it's the lowest energy level of the thing. That's why they stay together. As you pull them apart, the energy level will go up until it hits 0. That's where it breaks. That's sort of you hit your elastic limit. It goes up linearly. And as you hit your elastic limit and it starts to permanently deform, it levels off, and then it breaks and you're at 0. As you push them together, the energy level goes up as a function of 1 over r to the 12th. It goes up really, really quickly. And so when you collapse that in there, the Hamiltonian, which is a system of equations describing all the different types of energy within the lattice, when as you're pushing them together, that energy level goes up. You've got the confinement energy of making that proton into a smaller and smaller space. So that raises its energy level. And when the energy level of that first Brillouin zone, which is where the name of the company comes from, hits 0.8 and actually 782 keV, hits a large enough number, it converts that energy into the mass difference between a proton plus an electron and the mass of a neutron. That's very endothermic. It's converting energy into mass. It's sort of like a reverse nuclear weapon.
Right. Wow. So it builds rather than destroys.
A little ball of mass and turns it into an enormous amount of energy. We're taking an enormous amount of energy, but it's at the quantum. It's at the very, very tiny scale.
So I'm sorry, but you could recycle the nuclear weapons into energy sources. Is that right?
So we had Fermi. We had Fermi Labs. They wanted to do a cost sharing deal with us, which basically would have just completely drained all of our financial resources entirely. It was rather cynical on their part. They're like, well, we'd like to do a cost sharing program with you to eliminate nuclear waste. It's like, solve one of our problems, we're going to bankrupt you in the process of trying to solve one of our biggest problems. Maybe kill two birds with one stone. We'll put you out of business and maybe solve a problem for ourselves.
Having said that,
Oh, but does
there
it
is a
work?
project I'm familiar with called the Sapphire Project, and they think that their technology can remediate nuclear
the electric sun
waste.
And it may be able to. The Sapphire Project is really the Electric Sun project is really fascinating. I haven't spent a tremendous amount of time looking at it, but I have looked at it. It's really interesting.
Similar but different.
Wow.
Yeah.
Because they are using plasma, aren't they? And they're
Yes.
creating sort of what do they call it?
Self-regulating,
electric biolayers.
Yeah. Right.
And it sort of looks like increasingly wider and wider halos around the anode. Is that right?
Yeah. Right. So
Wow.
actually, I think it's the cathode is where is where the plasma is forming around.
Cathode. Sorry.
Yeah. That's
I knew I'd get that wrong.
That's okay. Because they're interested in the positive particles, so that you need the negative the cathode to bring them close by. And what makes a plasma is just that the binding energy of the electron to the proton in hydrogen is 13 eV. And so when you get above 13 eV, the protons are moving fast enough that the electron can't really stay bound to it. That's what forms a plasma. But we're just absorbing hydrogen into the metallic lattice, nickel. We're absorbing it into the nickel. So there's lots of electrons around it, but it's not actually bound. It can actually move, relatively freely through the lattice. And then and it hops. It's called tunneling. So you'll find it here or here or here, but you'll never find it outside of those areas. It's in very specific locations where you'll find it. And then we hit it with this shock wave, pinches it, turns it into a neutron. Now it's ultra cold. It's really, really cold. It removes that proton, that positive energy barrier, that positive charge energy barrier. Another hydrogen ion tunnels into that location. It tunnels into the exact location where the proton was, but it's now a neutron because that's where the hydrogen goes into these metals, is very specific locations. So it's already within the strong nuclear binding distance. As soon as it tunnels in there, and they bind. That's why even tritium will bind with a neutron under these conditions. But the whole thing is well below 1 eV. We're targeting the upper bound of where where the catalyst operates at around 700 degrees Celsius, which is still really, really hot, but it's well below 1 eV. Almost everything is a plasma by the time you get to 1 eV. That's really hot.
And how do you stop it from going bang?
So
it's hydrogen after all.
I was actually asking that too.
Yeah, good, excellent question. So the field in general is known as LENR, or low energy nuclear reactions, and what we're doing, we call it CECR, which is controlled electron capture reaction. So each time you put an impulse function through the catalyst to generate those neutrons, you've got some probability of having any one proton turn into a neutron. And we're in the process of raising the probability, so the more neutrons you create, the more energy you get out. But each impulse going through it generates a set of neutrons, and as they bind, they release energy. So as soon as you turn off the Q pulse or the ignition system, as soon as you stop the ignition system, within 1 second, it's over.
It stops.
Completely over, and no further energy if it's in a big machine, there's a lot of thermal energy mass. There's a lot of thermal mass that's still at very high temperatures, but no further energy is being added to the system. That's how you keep it running.
I mean,
away.
that's the problem with nuclear reactions, isn't it? It's once you start them, they're very hard to stop.
It's not even. It's worse than that.
Mm.
It's worse than that. The reactors at Fukushima that blew up, those weren't nuclear explosions; those were steam explosions. But in a fission power plant, you drop all the control rods down into the pile. Those are the terms of, in a nuclear reactor. Even when the reactor is shut down, completely shut down,
Still very
it's
hot.
still producing about somewhere between 1% and 5% of its nominal operating energy, because the stuff that's in there is fissionable and has a half-life. It'll continue to fission and generate neutrons. The control rods absorb most of the neutrons, but there's still thermal energy being created. So even though they were in cold shutdown, when they lost the ability to circulate cooling fluid through there, it got so hot, it started to split the water into hydrogen and oxygen. They weren't allowed to vent it because management said, oh, you have to run it through us before you vent it. And they're like, okay. And you got so much hydrogen and oxygen in there, eventually something, a spark or something caused it to detonate. And that's what actually blew them up. It was a hydrogen oxygen explosion.
And presumably that's still very deadly because you've got all the rods in there. And
right. Yeah. So it's not just hydrogen and oxygen up there, but there's a lot of radioactive tritium and all kinds of nasty egg.
And they stored the old stuff above the tanks, didn't they, as well? As far as I understand.
Well, yeah, right. Well, not above them, but off to the side. It's just outside, and it's no problem. Even those cooling pools still have to have water circulated through them, because even though it's spent fuel, it still produces all that really nasty radioactive waste, still produces a lot of heat.
A lot of heat, yeah.
And if you don't, keep cooling water over those rods, even those, spent fuel rods can still melt.
Mm-hmm.
They still produce a lot of heat. No issue, and there's nothing like that with reactors. You could, you hit a power plant using this technology. A meteorite strikes it, you'll get a steam explosion. The meteorite's going to do way more damage than anything to do with this. And as soon as it cools down, it's not, physically hot enough. You touch it, it doesn't burn you. There's nothing radioactive. You're not going to get any radioactive contamination or radioactive burns, nuclear burns. As soon as it's cooled down, you go in there with a backhoe and a bulldozer.
Am I right in thinking you're just producing helium, or are there other byproducts?
Helium is the only waste product, and any heat that you can't use.
There's a good industry for helium. Let's face it; they're constantly complaining that there isn't enough helium.
Yeah, actually, that's not actually true. Anytime you drill an oil well, the first big bubble of gas that comes out of any oil well that you drill is helium. The problem is it's not economic. If helium were 30 times more expensive than it is now, there won't be a shortage, because every oil company, they're still drilling hundreds of wells a day. And every company drilling one of those wells would be very careful to capture that helium and sell it. So if you were to build, say, a 3 terawatt thermal plant to generate a terawatt of electricity, it would take you about 5 seconds, assuming you could collect every helium nucleus that was produced, every helium atom that was produced. It would take you about 5 seconds to fill a party balloon. So it's not a good source of helium. It's just
okay, fair enough. But at least it's not dangerous anyway.
No, it's the biggest danger with this technology is burning yourself. Just the heat produced. That's the only danger. You might get shocked, We use high
Could you tell
voltage.
us about the wet? Because you've been telling us about the tubes, haven't you? But what about the wet systems? What's the difference?
The underlying physics is identical. The difference is in the wet system, there's something called cavitation, and so that's when water boils. You look in the bottom of your pot, and the water starts to boil. It's not under pressure, but it starts to boil. When you get really intense boiling, it's like cavitation, and as the bubble pops, it can, or even forms very rapidly, it can destroy the catalyst. So if you're using the wet technology, you're kind of limited to 200 degrees Celsius, because at 322 degrees Celsius, it's impossible for water to be a liquid. It doesn't matter. You can put it under, a bazillion PSI or KPa, whatever, and it will be supercritical. It's a different phase of matter, kind of like a plasma. So you're limited to about 200 degrees. That allows you to pull the energy off of the catalyst rod. 322 degrees Celsius is where it goes supercritical, irregardless of the pressure. So those were designed to operate at 1,500 psi in the pressure vessel, so you can get up to about 320 degrees centigrade before it goes supercritical at that pressure. But you can't really let your catalyst go above 200 degrees centigrade, because you won't be able to pull the heat off fast enough, and you run the danger of cavitation and destroying it. Also, you're dealing with caustic material in there that allows you to do the electrolysis. You've got a sealed vessel with hydrogen and oxygen being formed. Spaceship Columbia. It's a lot trickier. It's a lot more dangerous, because you do have hydrogen and oxygen gas. With this, there's pure hydrogen gas in there, and not a lot of it. So it's a safer technology. That one, the wet technology, is limited to about 200 degrees Celsius for the electrolyte. This one, you can go up to 700 degrees Celsius. So the amount of energy you can use from your heat source, the Carnot efficiency, is based on the delta T between where you're exhausting the waste heat to versus your source energy. The higher the temperature that you're operating at, the higher the efficiency, the more of that energy you can use. So the hot tube is just, clear winner on so many fronts. That's what
I see. Sorry, I was just going to say, what's the energy gain between the two systems? How much electricity you're putting in, how much you're getting out?
So we conclusively demonstrated twice as much thermal energy out as electricity in the pressurized water wet system, water electric tube system. That's not the limit. That was just as far as we got on that system before we decided to focus on the hydrogen hot tube. The best that we have shown so far with the HH2T is actually collecting more thermal energy in water than we're pulling electricity out of the wall, which you can't do with anything other than nuclear. You can do that, gasoline, right? But you're consuming quite a bit of fuel. Actually, any chemical fuel can do that, but you're consuming, chemical fuel.
Yeah. With
the system where we actually were able to collect more thermal energy in the water than we were pulling electricity out of the wall. It was stop flow. There was a small amount of hydrogen in there. The pressure didn't go down during the many hours that we were doing that for. So exactly how much, we're at like, 1.2, maybe a little over 1.2 times the amount of thermal energy collected in water than electricity out of the wall. But we did that once, and it caused problems. It actually caused the catalyst we're advancing the materials. We got the materials to the point where we're able to do that, but it burned the seals that actually hold the hydrogen around the catalyst tube. So we're in the middle of re-engineering how the catalyst tube is made so that that doesn't happen anymore. That's the material science that we're focused on now, as well as increasing the probability of generating neutrons, or the ratio of power out versus power in, which is your COP, coefficient of performance.
So it's an engineering problem now.
It's strictly an engineering problem. Yeah.
So, Robert, I know you're seeking to power conventional products with Brillouin technology inside. So that's like coming. But as far as focused on how this could, work with licensing for mining energy, before we run up on an hour here, I'm like a kid in a candy shop to hear more about what you think, how this could be applied to the energy consumption with, our ecosystem here.
Sure, absolutely. So this is nuclear technology. It generates heat. That's what nuclear technology does. It generates heat. But then you can harness that heat to spin a turbine to generate electricity. So you could have something the size of half of a shipping container that can generate 10 megawatts of, maybe a whole shipping container, 10 megawatts of electricity in something that size. So you could put that outside your mining facility or data center or whatever, and power the entire thing, not just as a standby generator, but that's your primary generator. And any energy that you're not actually using for mining, you could actually pump back onto the web. So you could not only do mining, but you could also generate electricity. And generating electricity is almost like printing money, because there's such a huge demand for it. The expectation is less than 2%, less than 2 cents per kilowatt hour. Because it's completely green, you could probably sell it on the grid in urban areas for more than 5 cents a kilowatt hour. So 10 megawatts is 10,000 kilowatts per hour. So if you're making 3 cents per kilowatt hour on the electricity, and you're doing 10,000 of those per hour, 24/7, that's a lot of money. And it doesn't matter whether you win the mining operation or not, you get paid for the electricity.
Yeah. No, it's a good point. And the great thing about it is it can be installed kind of anywhere, can't it? Because it's not reliant on natural resources necessarily, or the right conditions.
Absolutely. So right now, energy is a zero-sum game. If you put the uranium in your nuclear power plant, the other nuclear power plants can't use that uranium. If you burn the hydrocarbon, nobody else can burn it. You're turning that hydrocarbon into CO2, and it's a finite resource. This technology, hydrogen, as we mentioned earlier, is the most common element on the planet. So it doesn't matter how much energy I produce using this technology. It doesn't preclude anybody else from, producing as much energy as they want, regardless of where in the world, or on the moon or Mars or wherever they're located on their spacecraft. It's no longer a zero-sum game.
I just want to ask, I invited Kurt Wuckert Jr. To join us today, and he's moving into a new place, so he wasn't able to. So I'm positive we're going to probably have a follow-up with him eventually. But he did ask me one question in a messenger thing. I just wanted to throw out there and get your response for him specifically. It said mining requires another and consistent power delivery. Yeah. Supplementary power tends to fluctuate in availability. How can we do this? How can we do better with this?
So this is nuclear technology. Does not matter whether it's rain or shine, underwater or in outer space. It is consistent, reliable, stable, steady state power. And it's got an accelerator pedal on it. It's got an ignition system. You push down on the accelerator, you get more energy out. You let up on the accelerator, you get less energy out. So it is dispatchable. So in electricity terms, that means when you turn it on, it's on. When you turn it off, it's off. You can turn it up, you can turn it down.
Okay.
So it is really.
How does it travel?
Oh, it's just electricity.
Does it go
isn't
through?
it,
Does it
Rory?
go through a pipe or does it go through a wire?
It
How
goes
does it
through-
go from this generator to the turbine to the source, the resource?
So there's a number of different things. So one of the really interesting things is Stirling engines. You've got a hot side and a cold side. So in this case, you're producing heat that goes through the Stirling engine, and what the Stirling engine doesn't produce to shaft horsepower, which spins a generator or whatever to generate the electricity. The electricity travels through wires, but this just produces heat. So you can transfer that heat with a gas, with a liquid, supercritical CO2, direct thermal conversion, which takes heat and puts it through a Peltier, something that converts heat directly to electricity. Those are right now, I think the best they've seen is like 7% conversion efficiency. So you need more than 10 times more thermal energy out than you would get electricity out of the system. But
does it go into the rig by a wire, or how does the energy actually get into a computer or a cell phone or
okay. Well, so
the actual subway
right.
system?
Right. So that uses electricity, and so in a cell phone, we'll have to, before it can actually go into a cell phone, you might be able to miniaturize something like supercritical CO2, where you've got your Brillouin heat source heating the CO2 that goes through the little turbine inside your phone, and if you're drawing a lot of energy, just like your battery gets hot, you'll have to dissipate that waste heat out of the cell phone, and that's how it gets there. So it's a heat source. And the more efficient your conversion technology, so like the way it gets from the reaction to electricity is it has to go through the heat, has to go through something. So you take your teapot and then it starts to whistle. You can take a little fan hooked up to a little DC motor, and the steam will spin it and it'll light an LED.
That's the funny thing about it, isn't it? It's fundamentally electricity generation does tend to be quite low tech when you get down to it. It's all about boiling tanks of water and turning turbines,
much,
isn't it?
Yeah.
Even nuclear power is the same.
Yep.
It's all about just creating heat energy and
Would
then
it
harnessing
eliminate
it.
wires? Would it eliminate the need for wires?
No, it's still just normal electricity, Rory.
Yeah.
Same as you get now. I mean, nothing would change. You'd have a power station that was basically connected to the grid, the same as any other power station.
Right.
So there's a plug at some point.
Well, so right now your cell phone runs on a battery, right? You have to plug it in, that charges the battery up, but there's wires connecting the battery to the rest of the cell phone.
So explain to me, Robert, though, because you were saying when we started talking originally, I asked you about cell phones because there was something that I heard where you were saying, wouldn't it be great if your actual mobile phone could actually then?
Right. So right now you plug your cell phone into a charger, and you plug it into your little charger there, and it charges up the battery. And then you've got some efficiency, and then throughout the day the power in your battery kind of goes down and down and down and down, and then you can't use until you plug it back in. With this technology, the phone would run until it was just too old to work anymore. As they upgrade, you go from 5G to 6G to 7. By the time they get to 7G or 5G, phone probably won't work anymore because it just doesn't. The radio is not capable of communicating with the new infrastructure.
So it would just kind of recharge itself, and just continually going and going and going until, like you said, that battery eventually dies completely.
Until the rest of the phone is gonna wear out before the power source wears out. It doesn't continuously charge; it continuously produces energy.
So for a consumer of mobile phones, that would be the best possible solution. But obviously, for the people who are making the batteries, I suppose they're not overly fond of this technology in that respect. Then,
actually, they're very complementary. Because this is an external combustion technology. So like take a car, for example. when you step on your car, when you step on the accelerator of your car, you want to go now. You don't want to go in 5 minutes after there's a lot of thermal mass involved in that. So you step on the gas or you increase the output of your reactor, and it starts heating the stuff until it gets hot enough to spin the turbine faster to give you the power to make your car go. You don't want that. You want a battery. So you step on the accelerator, the car starts to accelerate immediately, and the turbine spins up. You start producing, the more heat. And then once the turbine's up to so you step on the gas, and initially your battery is supplying all the energy, and then as your turbine comes up in power, it goes like this, and now your turbine is producing all the energy to run the car, and the battery's just kind of there. Maybe you don't discharge it until you charge it part way up, and then when you step on the brake, maybe you do regenerative braking, and a combination of regenerative braking, you turn off, you take your foot off the accelerator, but there's still all that thermal energy that's stored in the system. And as that thermal energy dissipates, you use that to charge the battery up, and now the battery's at full charge. So the next time you step on the gas, it's ready to launch you from the dead stop. So the batteries, you're still going to want batteries, but you don't have to worry about a supercharger station.
That's the thing, isn't it? Because all these systems require energy to be fed into it in order to create more energy. Correct. So they all do need to have
this is exactly the same. That's what's unique about this nuclear technology, is that you have to feed energy in to get more energy out. But as soon as you stop feeding energy in, it stops producing heat.
Right. So
you can turn it off. Perfect. As opposed to an existing fission plant, you drop the control rods in, it's still producing heat. You have to use electricity to pump water through it to cool it down,
Yeah, and then if you have to decommission the plant, you've got a big problem that goes on for
huge problem,
thousands of years potentially.
Yeah. Right. So at the very start of this conversation, you said about flying cars. I'd like to get your opinion of the flying motorbikes that have been, which Casey brought my attention to the other day, flying motorcycles. So obviously you need a PPL, which is a private pilot's license, to be able to fly one. But we're at that point now where you could actually go out and you could at least buy yourself a private flying motorcycle. So we're at the point, I think you wanted to be in 1992 then.
I was going to say, it was jetpacks back in my day, wasn't it? We were all expecting we were going to have.
Yeah. Sure. Yeah. So, I mean, this technology, because it does give you, nuclear power on demand, completely safe green nuclear power on demand, cars will stop using roads. They'll turn into long, green parkways. Little parkways where people can, play whatever on them, and cars can move freely in 3 dimensions. This technology will allow that.
So do you think in the UK recently, there's been quite, and obviously over the world in the last 18 months or so, there's been quite a lot of disruption on the roads, and obviously less and less people, being convinced. So do you think this is kind of the shift to try and get people's mindsets into, you don't need to fill your car up with petrol because we're going to be flying soon? Or do you think it's still going to be a very niche kind of market for people? Or do you think this is the point where the governments are trying to basically get our mindset ready for flying cars and being able to personally fly without a plane, etc.?
I think you're giving them far more credit than I don't think they're that smart.
I watched too many sci-fi movies.
Your lack of planning is not my emergency, sort of a thing. It is actually everybody's emergency. Their lack of planning and not really thinking through Brexit and we're going to get rid of all these truck drivers so we can hire local people. Oh shit, nobody wants to drive a truck.
And we haven't done any driving licenses.
Nobody was thinking about energy when.
No. So Robert, go ahead, Diddy. Sorry.
Well, I was just going to point out that there are autonomous trucks, in Europe already anyway. So this is part and parcel of that kind of taking away the jobs from the drivers themselves and actually replacing it with autonomy. So
you're still a few decades away from really being able to do that ubiquitously.
Especially on European roads, I think. I mean, American roads are a bit easier.
Well, Italian roads, French roads,
European roads, not so much.
Yeah.
So, Robert, where are you guys at with funding and getting this like out to the masses and mass production? And how can the BSV community help with that?
So, right now we've always, David Furshine is my CFO, and if it wasn't for him, we wouldn't be here at all. But because of the challenges in raising money, I actually had to cancel. I was going to buy 100 Bitcoins, what was it, a year and a half ago? It was down, below $4,000 briefly. It was, right around $4,000. I actually had a buy order in for 100 Bitcoins at $4,000. I had to cancel because I had to take some of my working capital and put it into the company to keep us running until he was able to bring more money in. So it's very, very rare. I think it's in the 13 years that we've been in operation, there's maybe 3 months where we've actually had as much as $1 million in the bank. So we're, yeah.
I was going to say, so I apologize, but shall we educate Robert on Bitcoin?
Yes, let's little. Give us 5 minutes of your brain space, Robert.
Yeah. I mean, the first time I got active in Bitcoin in 2010, and actually I've put more than $1.5 million into Brillouin Energy because I bought about 300 Bitcoin when it was below $100. Yeah, and
that was a good investment. Well done.
It was by far the best investment I ever made.
Which you have the opportunity to do that again with BSV right now. Just saying.
See, BSV is Bitcoin,
even lower
Robert.
than $300.
Robert,
I told you. I mean, at least 6 months ago to a year ago, I remember having a conversation, telling you that BSV was the bee's knees and that you needed to pay attention to this ecosystem, but we're here now, so I'm just really excited that.
I tell you what the problem is, Robert, is that we share a lot in common with Cold Fusion in as much as they're trying very, very hard to discredit Craig Wright and BSV and sort of pull attention away from it because it's the only one that can really work at scale. Bitcoin SV could onboard the whole world and already can do, what is it now, 50,000 transactions per second? Whereas BTC is...
it's been demonstrated at 100,000 transactions per second and at 3 gig blocks, and that's on the test net. But actually on the main net at the moment, we are on 50,000 transactions and 2 gigabyte blocks. And they said that this was not possible anyway. They're stuck on 1 meg blocks with 7 transactions per second. But we can actually do all of world trade 50 times over on BSV. Now, when you consider what all of world trade actually is, that is a phenomenal amount. And this is what is possible with unlimited block sizes. Plus also BTC was hijacked. It is no longer Bitcoin. It is something completely different. And that again is one of the arguments. It's not what it says it is in the white paper. It's a peer-to-peer cash system. And with a cash system, that also means that you can do other things with it other than just hodl money. Does that make sense? Like, there are so many different variants that you can actually do with this technology as well. So I have to just put my 2 pence in there that BTC is not actually Bitcoin anymore. It's been changed so much from the original white paper.
No, I recognize the difference between BSV. I actually hold 0 crypto at the moment. Like I said, I wanted to buy, 100 Bitcoins back, and the
we had done that.
wouldn't tell you that was a bad idea because it wasn't. But on the other hand, BTC can only do 6 transactions per second.
And I
And you see
whatever.
the-
We're talking minutia here, and
It's
I
yeah,
totally
it's the
recognize that.
system. So
Right.
if you,
And
Robert,
guys
you're
are
very
both-
technical. If you go to section 2 of the white paper, then you can see we define an electronic coin as a chain of digital signatures. And in 2017, software developers implemented segregated witness, or SegWit, which removed the chain of signatures. So therefore, what is commonly seen among people as being Bitcoin in the trendy sense
that
is
broke it.
no longer at the actual mechanical sense.
Right.
So that's why we are really, sticking to the point that BTC and the prices thereof, that's just hype with no utility.
Yep.
And Bitcoin is a system that offers great utility. So therefore, we can have the utility at high levels of efficiency, which outcompetes all of the other industries, whether
Yeah.
it's the cloud or whether it's other markets. So I think that it's great that you had that good opportunity to invest in capital for your business. That's a blessing, and hopefully then you can also let us know what you need, how we can help you to
Yeah.
maximize what you have done with your
Sure.
invention.
I was going to
Sure.
say
Because
it's
we are
probably
sticklers for the details. And so we want to understand, what is it that you've invented? Is it market ready? When will it go to market? And how can it benefit our ecosystem?
Sure. So we can actually have this technology to the point where it could generate electricity and power everybody's mining equipment in 18 to 24 months. Once we have enough capital to put all of our manufacturing facilities under one roof. That's going to take sort of $35 million is the minimum to put it all under one roof. Give us 18 months to have the technology ready for integration, 36 months before it's actually shipping to mining operations, and drastically lowering the cost and greening the entire operation with a solid, steady state source of energy. As it is now, as usual, we have less than $1 million in the bank. But we're going gangbusters in our 1,200 square foot lab on the 3rd floor of a building built in 1905. Yeah, historical
Historical architecture.
Yeah, actually have a walled over what used to be a coal-fired power place. Coal-fired fireplace. Yeah. There's actually 2 of them in my office. So capital is what makes this go. If somebody, I know there's quite a few people with a lot of cash or net worth, very high net worths. If somebody or a collection of people put together $35 million to allow us to do that, we would be happy to work out some sort of a licensing agreement where they get 30 years of royalty-free access to the technology to power their mining operations and or sell electricity onto the grid, which is also like printing money.
That would be amazing. We do have
yeah,
people in BSV who think very long term,
yes,
Right.
and who are building, huge infrastructure out, tile mining,
that's what I
Calvin
was
Air. Craig Wright himself is, very future orientated. He's in it for the long haul. He's going to be doing it till he drops dead, I'm sure.
And even if they don't have $30 million, just allowing us to right now our burn rate's around 200K a month. And so even just just buying stock in the company, buying stock in Brillouin Energy is probably like buying BSV at $5 a coin.
Oh, what is your information for investor relations? Let's look it up, because I know Tal is on the what
Yeah.
it was, it's SQRMF or something before on the Canadian Stock Exchange.
Oh.
Are you on NASDAQ or NYC? What are you
No,
on?
no.
How do people get shares?
We're on the web at www.brillouinenergy.com.
Oh, okay.
And
go to
you
the
can,
website.
you can.
It's just private investors at the moment, is what you're saying.
It's
Oh,
a
okay.
private company. We've got I think about 70 investors. We have
Cool.
raised a grand total of we're a little shy of $22 million since 2009. But with that money, we've actually got 5 reactors running in the lab right now. This is a very, very straightforward technology. So, that's what it takes to develop this technology into develop this phenomena into an actual deployable technology. It takes cash. And we're developing, you look at these small modular reactors, that takes literally more than $1 billion to actually create one of those that can be deployed.
No, that's a really good point, actually, because we've like prepaid, I think, for some nuclear energy in France at the moment, in the UK.
Oh, yeah.
And we paid through the nose for it. I mean, it's ridiculously overpriced.
Yeah.
And so already a white elephant. So yeah, no, it's a good point to do a side-by-side comparison of how much it would take to get you up and running versus your average nuclear power plant, which is billions and billions.
Right.
So,
and growing.
As we said, the third world countries as well. This is a phenomenal kind of opportunity.
That's what I was just going to bring up. Is Dr. Craig Wright the other day said that he was willing to donate the 100 million Bitcoin or 100 billion, whatever it was, the Bitcoin that he had,
million Bitcoin,
billion poorest people in the world. And I just was thinking that this, it could be a part of that philanthropy.
It really could, yeah. This would make a lot of sense.
Really, amazing way. So on the bottom, the ticker is your Chief Financial Officer, David Fearshine, his phone number and email address. So we, Robert, are honored to make sure that this gets seen by some of the key people that could actually help propel this technology with you for humanity. So thank you. I'm just I've been working on this with you for 4 years now, trying to get this.
I think it's longer than that.
In front of the right people. And when we had tried to put this into an ICO before, it just wasn't the right timing. And I think now is the right timing.
The right people.
We just had the 3-day CoinGeek conference that was all about time and how it's about time. And humanity, we need this technology. We
need to advance it fast. I mean, the hydrogen to me is such a fascinating area of study on all fronts, not just energy creation, but for health as well, and all sorts. But I just think your moment has arrived, because awareness is really starting to increase, isn't it? People are starting to talk about going back to nuclear energy, favoring nuclear energy, and we can do so much better than that.
Absolutely. Absolutely.
And I have a feeling that the same people that are blocking BSV are probably the same people at the highest levels that are blocking you. And you've got a whole community ecosystem of activists that do not want that anymore. So there's got to be some way we can come together as a community here and make sure that this gets, it's about time that this gets, implemented.
Really is.
So I'm just got my fingers crossed for you. We're praying for you, and
great.
Yeah, I'm impressed, very impressed.
And thank you so much for your time.
I did have
it's an honor to meet you, Robert.
Thank you.
As you were explaining things earlier, I thought you're a really good teacher, and chemistry is something that people can maybe tune out of while they're in school. But if there were someone, if it was you, giving some lessons, even basic chemistry lessons on the internet, I feel like that is something very meaningful, because you could maybe inspire new engineers to come into your market. And also curious people could learn a lot from you, because you've sparked a curiosity for all of us today.
Thank you. I'm I'm thrilled to hear that. But I'm typically putting in, 60 hours a week, sometimes closer to 80 hours a week. But you can't do that and maintain your health for too many weeks in a row.
Mhm.
So much as I would love to do that. I just don't have the time.
You need to make sure your knowledge is passed on,
Mhm.
So we've got a
Don't let that
really,
die with you, for
Mhm.
sure.
really great team of people, and I've started working on hiring some younger people. I just hired a gal that just got her degree in mechanical engineering from UC Berkeley. Had a degree in physics from one of the universities in Southern California, and she's a very sharp gal, and there's I'm working on it, working on getting more people. I'm up until I hired her, I was the youngest person in the company. I'm 57 now.
You
You
don't look
spring
it.
chicken. Listen, this is the future. Anyway, I would love to see you whiteboarding. That's all I'm saying. I really want to see you at the whiteboard teaching. I would get so excited to keep watching and learning more and more.
I always think electricity is the hardest subject. It's just the hardest. Do you think? I mean, perhaps not
Well,
to you.
and it's the
but
most
oh,
controlled. Look at how long we've been kept under the enslavement of energy corruption. I mean, back from the Tesla inventions that were, stifled. We should already have such a more, safe energy grid than we do.
Yeah,
It's-
we
it's-
really should.
It's insane that this has
We've
been going
lost
on so
time.
long. Yeah.
Yeah.
So,
we would love to anybody that wants to invest personally. We still have, I think, about $3 million left in our Series C round.
okay.
If there's deeper pockets out there that are already spending a lot of money on electricity to do mining,
Mhm.
we would love to talk a license or a combination of license and investment.
Mhm.
Sounds like an amazing opportunity. It really
It,
does.
it really is. It really is.
We'll keep pushing for you because we believe in you. We believe in this product and technology, and are very grateful for all of your hard work.
Well, thanks for having me on. It was great talking with y'all.
You too.
Thank you very much,
All right.
Robert.
Have a good
Thank
afternoon.
you.
Yep.
Robert got us. Thank you.